The second mode of heat transfer that we would like to analyze is convection. Convection is the movement of molecules or pockets of molecules from one spot to another one, as opposed to the vibration of molecules at their fixed location. And generally speaking, for convection heat transfer, understanding requires the energy balance. So requires energy balance and analysis of fluid dynamics. Or fluid motion. We generally look at the steady state conditions, and what happens in convection is the temperature gradient inside the fluid rise to a flow of heat or results in the flow of heat. Now, the rate of heat transfer by convection is much larger than the rate of heat transfer by conduction alone. And what we will be focusing is in the next few lectures, we will be focusing on the principle of convection. Then we will look at the forced convection. And in forced convection, we will look at the external flows. For example, flow over a flat plate or over a pipe or a collection of a pipe, or we will look at the internal flows, such as flow inside a pipe. Then we will look at the free or natural convection. And we will consider convection with phase change. And we will be only looking at the boiling and condensation. Ultimately, we will use the learnings in the heat exchangers. So we look at the convective heat transfer in heat exchangers. Now, recall the Newton's law of cooling that we use for a convective heat transfer boundary conditions. And what we had was, we had a solid surface with the temperature of Ts, and then we were saying that there is a flow with the velocity of u infinity t infinity that's flowing over this surface, and there's going to be heat transfer from the solid to the fluid, or fluid to the solid. And for this convective heat transfer, we're using this Newton law of cooling, which is Q H Ts minus T infinity As. And that's the area. Now, one part here is that in all analysis that we are doing so far, we're assuming H is given, but really where H comes from. H is the convective heat transfer coefficient. And we have to evaluate flow over a surface in order to obtain or determine H. So the way that we determine H is we have to flow, fluid flow over solid surface order to determine H. So inherently, this is a fluid dynamics problem. Now, when we want to evaluate that one, we can get H by when let's say we solve the flow equations over a solid surface for simple geometries, laminar flow, we can have analytical solution. And through these analytical solutions, we can obtain H, the convective heat transfer coefficients. However, the solution is very limited to a few cases. That we can really develop an analytical solution mainly on the laminar flow regime. And the other way that we obtain H is by empirical data. That we get from experiment and they have a wide, I would say, applications or these are widely used, the empirical data to obtain H. In general, H depends on fluid properties. For example, it depends on density of the fluid, viscosity of the fluid, thermal conductivity of the fluid, specific heat capacity. Essentially everything that is related to the fluid properties. It also depends on the surface geometry. Surface geometry of the solid and flow condition. So in the following, we will have a brief review on the fluid dynamics principles on the flow over surfaces in order to obtain and understand how to evaluate the convective heat transfer coefficient.